Thank you. Thank you for the invitation. Please do indeed ask questions. There are many ways I could give the talk, depending on the audience. So if you ask a question, I'll figure out what you're most interested in. Okay, so I'll start with some motivation. This is a story due to William Goldman. I was supposed to look up in advance if he spells it with one N or two, I don't remember. Okay, so the setting is the following. So sigma is a closed oriented surface. In the sense of topology. And the orientation, I'm going to actually fix that. It's not just orientable. I want the orientation fixed because I'm interested in Poincare duality. So this is some class in second homology. Doesn't matter too much where we take it, but I'm going to take it with complex coefficients. And Poincare duality then remember that it says, so there's one way to say it is I could look at homology of the surface that acts on homology. In particular, I can act on this fundamental class that I've chosen, this orientation. This gives a map to homology shifted up 2 degrees. And this is an isomorphism. So this is one way to state Poincare duality. More generally, I'll have a version of this with local coefficients. So I'll come to that in a moment. And we want to study a moduli space associated to this. So this is going to be, I'll write it heuristically just as a set. I'm telling you what the complex value points are, but you can do this in families. So these are representations of the fundamental group. I could choose a base point. I'll leave that implicit. So I'll look at representations of the fundamental group of rank R. So that's a set. And maybe I want to consider it up to isomorphism and consider some coarse moduli space, or maybe I want to remember all of the automorphisms and isomorphisms between them, and then I get some group point. So this is either called the character scheme or stack, depending on what you do with automorphisms. In this motivational section, I won't care about it too much. So it parameterizes representations. And if you think about concretely what this is, you could present the fundamental group by generators and relations in your favorite way. There's a standard way to do that. And so then you're just giving as many invertible matrices as there are generators, and those matrices have to satisfy some relations. And then maybe you take the quotient of that affine variety by conjugation by GL. So this gives some moduli space of rank R representations. And we know that there's a more, so that's the algebraic description of what points of this moduli space are. But there's also a topological description of representations. So these representations can be thought of as monodromy for a locally constant shape. So this is rank R local systems. Maybe, for instance, from that connection. Okay, so that's a useful way to think of them, and I'll write the notation in a row. Local system is written E rho. Okay, and I want to involve, there's also, in fact, a Poincare duality for local systems. This is PD duality with local coefficients. This is maybe a little less familiar. Maybe it's not in your first book on algebraic. Says that I can formulate it kind of more in the style of Serre duality, if you know what that is. So I can look at derived endomorphisms, the R-HOM from my local system to itself. I could compose two such things. And then I could take a trace. So on the fibers of this local system, I just have some matrices. I can take the trace fiber-wise, and I'll get an endomorphism of a constant sheaf. And this, what is this? This is all the orientation. I get a map. So what is this? I get a map like this, and then the statement is that this is a non-degenerate pairing. This is non-degenerate, kind of graded symmetric in the Cazul sense. Pairing. And so the x are dual to each other. X1 is self-dual and x0 is dual to x2. So why is this relevant to this moduli space? Is we can identify the tangent space to a representation in this character stack. It's a typical thing when you're setting a moduli space of some kind of objects and you have a point on that moduli space. The tangent space is given by deformations of the object, first order deformations. And when you're studying modules or representations, the first order deformations are given by the x1 from that object to itself. So these are the first order deformations. So this is a simulation. And putting these two things together, it says that this Poincare duality pairing, like I said, it pairs x1 with itself. And because of this graded symmetry, if I do the shift, it will become antisymmetric. So the theorem A of Goldman, with one or two n's, I don't remember, says that the Poincare pairing up above on x1 so let me write that. As T row, I'll suppress the name of the moduli space. So this is 2. And if I shift the R-HOM down by 1 so that the x1 lives in degree 0, I have to do that twice because I've taken the tensor square. And so this C shifted by -2 also gets shifted down by 2, and the pairing just takes place with coefficients in C. So there's this Poincare pairing. It's non-degenerate. Because of the shift, it turns out to be antisymmetric. So this is a 2-form on the tangent space. And I put them all together.
I think your screen sharing, Chris, your screen sharing just stopped.
Stopped? Yeah, I accidentally, let me try again. I accidentally closed the screen. Let me try again. Delete. Okay, so this Poincare pairing gives. Is it working again?
It's coming. There's a little bit of a lag, but now it's here.
No, we can see.
Okay. Okay. So this Poincare pairing gives a symplectic form on this character stack. So if you've looked at the paper of Goldman, he won't say character stack, he'll say maybe character variety or character manifold, and he'll restrict to representations with simple endomorphisms, just scalar endomorphisms. So that's a kind of simplifying the assumption that allows you to kind of ignore automorphisms of your representation. But if you're willing to work with the character stack, then the statement just works as I wrote it. So we have space, and if we, given some natural symplectic moduli space, it's reasonable to try to do some kind of Hamiltonian dynamics on it. So these things, such symplectic moduli spaces, are often related to problems in mathematical physics, and in very simple cases, you then get complete integrable systems. So we want to consider Hamiltonian dynamics on this moduli space. We want to think of it as a phase space. And so we need to say how stuff evolves in this phase space. We need to give some Hamiltonians some functions and compute their Poisson brackets. So the symplectic form determines the Poisson bracket. And it turns out that there are a bunch of natural functions on this moduli space that come from the topology of the surface. So, so here's some Hamiltonians. These are Hamiltonians from loops on the surface. So let's suppose I have a loop, just continuous map from the circle into my surface. I don't care about the base point. I can let it move around. And I'm going to associate to this a function. So define a function. Now I'm going to be a little bit floppy and just tell you what it is on the complex value points, but again, you can do this in families. So it's going to depend on gamma. I'm going to call it big F of gamma. What is its value at a representation? Well, I pick that representation. I can choose a base point for the loop. It won't matter. If I choose some base point for the loop, maybe that doesn't hit the base point that I chose for my fundamental group, but I can take a little path kind of to my base point and back again. So I can make sense of rho of gamma. That's just some R by R matrix, and I can take its trace. That gives a number. This is called trace of monodromy. I think that Goldman maybe calls it trace of holonomy because maybe he works with connections instead of local systems. So that's a function for each gamma. And Goldman studied the flows of these things and wanted to know when, for the corresponding Hamiltonian vector fields, and wanted to know when they commute. So we need to compute brackets between them. So we want the Poisson bracket. To see to what degree the two corresponding Hamiltonian flows commute or don't. So the second theorem of Goldman says the following. So first, a few observations about these functions. One is that because we're working with the fundamental group, those are homotopy classes of base loops. This value of this function doesn't really depend on gamma, it just depends on the homotopy class of gamma. And it also even only depends on the free homotopy class. I can forget about the base point. Basically, because the trace is conjugation invariant in the way you change from one to another by conjugation in the fundamental group. So, so the first observation, this is again Goldman, is that homotopy classes of free loops, so these are going to be formal linear combinations. These are linear combinations. Homotopy class of free loops. So L sigma is the loop space, the free loop space, just maps from circle into sigma. F is actually a map. Best thought of as a map from here to here, two functions. And on the right-hand side, we have a Poisson bracket. So we want to figure out how to compute that Poisson bracket on the right-hand side for functions that arise from loops, somehow in terms of the topology of the loops. So the statement is that the left-hand side has a Lie bracket. Of course, Goldman didn't call it the Goldman bracket, but everybody else does. And the way it's computed is, if I have two loops, I choose the position with the other, so they should intersect transversely. I can then the homotopy class, and then I'm going to sum over these transverse intersection points. So let me write, that's the, I think, traditional notation for transverse intersection. So I have one loop and then some other loop, and they intersect at 2 points. In this case, this is maybe alpha and maybe beta. And for each of those intersection points, I could consider it as if it were a base point of the loop. And then I could follow the loop in the positive direction, starting from that base point. So given that, I could concatenate them at P. So start at P, go around B, and then start at P again and go around alpha. And there's some signs depending on the orientation. So the intersection is either positive or negative. So the first statement is that this is a Lie bracket. So you have to check that this is well defined in homotopy classes of loops and satisfies the Leibniz identity. And so this is statement A. And statement B is that once with respect to this Goldman Lie bracket, this map, which takes trace of monodromy, is a map of Lie algebras. So it respects brackets. So F of the bracket of two loops is the Poisson bracket of F of alpha and F of beta. So the left-hand side is topological, even homotopical, and the right-hand side is symplectic geometry. So of course, a general function on the moduli space, you don't know how to compute Poisson brackets between it and something else, but functions that arise in this way, you can understand. And a lot of functions arise in this way. So it's a kind of subtle question. What is the commutative algebra generated by these functions, and how much of the full algebraic functions does it see? Okay, so this is the second theorem of Goldman. So all of this takes place in two papers. I think one of them is basically about the existence of the symplectic structure, and the other is about these Hamiltonians in the flows. This is a classical story of Goldman, and let me pause for a moment to see if there are any questions about these statements. So this is the picture I want you to find.
So can I just ask one question? When you talk about the tangent space of the moduli space, so you're using this in the stacky sense here, or you don't care too much?
So in this motivational section, I don't care too much. If you want the kind of simplest case in which this makes sense and you don't have to worry about subtleties, you could do what Goldman did and restrict to a subset of the moduli space, which is basically smooth. So the condition is that there are only scalar endomorphisms of your representation. So it's a simple representation. And then the dimension of the tangents on that piece is constant, and you parameterize these things by in a chemical way because they're all identical. Trace things in that. For purposes, it's really better to work with this kind of considerable representations.
I think the connection has gone very bad. It's been very different. Is that just me, or Frank? Was it for you too?
I couldn't hear much, actually. Yeah, I think there was a problem.
Let me try to change some connections. I'm sorry about that.
That's all right.
Give me one moment.
Sure.
You hear me?
Can you say something?
Yeah, I'm here. Can you hear me now?
Oh, much better actually at the moment.
Is it? Okay. Give me just one moment to plug something in. Sorry about that.
Okay, no problem.
You can ask questions as we continue, as I plug things in.
Actually, I had a question about this map F between these two Lie algebras.
Yes.
Is there anything now in injective, surjective? Did you say it and I just
yeah. So this is a subtle question.
Sorry, the connection again is so bad I couldn't hear what you said.
Is this so bad?
Okay, try again.
See my screen?
Yeah, there's a lag in the screen sharing as well because we just have the we don't have the slides back. Oh, it just completely dropped.
Oh, yes.
I'll run downstairs.
Yeah, the connection dropped. I don't know if you can see and hear us now.
Yes. Yes.
Okay.
If you give me 2 minutes
Sure.
to move. If you give me 2 minutes to move.
Okay.
I might want to pause the recording.
Oh yeah, we'll edit it later, so not to worry.
Okay. Okay.
Yeah, just to the audience, a bit patient to see that we get the connection back. So we'll continue.
Okay. How's that?
Let's see. Can you say a little bit of something?
Let's see if I'm sharing my screen still. So, can you see the screen?
Not yet.
Okay. Still not yet?
No, still not.
Let me try stop the screen sharing and start it again.
Okay.
That sometimes works.
No, it's working.
Okay. So let us try again. Okay. Okay, I hope there are no further problems.
This looks good.
Sybil asked about this homomorphism and to what extent is it surjective? So as I wrote it, it's not very surjective because, for instance, I could take products of these functions and then sums of products. So the left-hand side is Lie algebra, the right-hand side is a Poisson algebra. So a better question to ask is, if I take the symmetric algebra on the left-hand side on this Lie algebra, I get a Poisson algebra. Symmetric algebra of any Lie algebra is the Poisson algebra. You just write down polynomials and expand the Poisson bracket using the Leibniz rule. So then this has a better chance of being surjective. And I think the statement is that as the rank goes to infinity, this becomes surjective. But this is a subtle question about which I don't know very much. So this is an interesting and subtle question. People have done lots of work on it. I don't know what the perfect answer is. But
Okay,
there are some kind of stability results as the rank goes to infinity. Okay. So that was the motivation. And let me give you kind of the goal. So my goal is to generalize this picture in a few ways. So I want to, most of all, I want to consider two non-commutative manifolds. I'll have to tell you what I mean by that. Non-commutative closed-oriented manifolds. This is where the Calabi-Yau categories will come in. Two, I want higher dimensions. So as working with surfaces, I want higher dimensions. And because I'm doing higher dimensions, these moduli spaces become much more complicated and much farther from being smooth. And so it becomes very important to consider the tangent complex on them and to work in derived algebraic geometry. And once you're doing that, you really ought to do, and you can kind of only do things at the chain level. So here I was considering just functions in degree 0, and I was considering H0 of the free loop space that appeared in this Goldman-Lie algebra. I want to do everything at the chain level. So on the left-hand side, I'll have the chains on the free loop space. On the right-hand side, I'll have R gamma functions on some derived moduli space. So let me first deal with part 1. How do we introduce non-commutative manifolds? So there'll be two theorems that are kind of generalize the two theorems of Goldman. Right. So the idea for one is that if you look at what I did, I didn't need to know a whole lot about the surface. I was really interested in local systems on the surface, and those form part of a differential graded category. I could consider, say, DG modules over the fundamental grid. So the idea is to replace the surface with local systems on the surface. So these are derived local systems. And so you could think of those topologically as local systems of finite dimensional complexes of vector spaces, or as D modules, DG modules over the fundamental group. And I need a replacement for the orientation. And so I should say I'm going to consider this as a DG category. This is as a DG category, where the X between local systems give the DG structure. And I need the replacement for the orientation. And so I want something that's going to work for a general DG category. So C is going to be a smooth DG category. What that means is, for instance, if it's DG modules over a DG algebra, it means the diagonal bimodule is a perfect DG module, has a kind of finite resolution, so to speak. And then the definition, I want a kind of Poincare duality to be holding in this category, but it's going to be a kind of funny Poincare duality. It's going to be not for cohomology and homology, which don't make sense for DG category, but for Hochschild cohomology and Hochschild homology. So we say a weak, I'll tell you what strong is in a minute, a weak orientation or Calabi-Yau structure on C of dimension D it's a class. I'll write it as if it's a fundamental class. Where does it live? It lives in the D Hochschild homology of C. Such that, so I need something like Poincare duality. And remember how I formulated Poincare duality. It said that capping against the fundamental class gave an isomorphism between cohomology and homology. And here I can say the same thing, except for Hochschild homology and cohomology. So Hochschild cohomology acts on Hochschild homology. There are formulas for that if you have your favorite complexes for these things. Or if you think of Hochschild cohomology as endomorphisms of identity functor, and Hochschild homology is trace of identity functor, then endomorphisms of identity act on trace of identity. So the condition is this is an isomorphism. This is a kind of non-commutative Poincare duality, if you like. And what makes an orientation strong orientation is additional data So Hochschild homology has extra structure. Classically, Kohn constructed something that people call the big B operator. So this is a kind of additional differential that goes the opposite way to the Hochschild differential and satisfies some relations, giving a mixed complex. The more invariant way to describe that is that the homology of the circle acts on Hochschild homology. So I want the circle or the B operator to fix my fundamental class. And that's kind of homotopical data that has higher and higher corrections. So this is why it's additional data. And concretely, if you want an explicit complex that describes this, what this means is that this fundamental class should lift to, and you should provide the lift, not to Hochschild homology, but to negative cyclic homology. So this is more or less by definition the circle invariance on Hochschild homology. And so I can forget that something's invariant and get just the usual Hochschild class. And so I want a lift of the fundamental class to an invariant fundamental class.
Chris, there's been a question in the chat to remind us again of what a smooth DG category is. I think you said it, but
I did say it, so let me write it down. So remark. I could give an abstract definition, but let me just give the one that works in examples. So if the category C is R DG modules or some DG algebra, then C is smooth if and only if a diagonal bimodule is perfect over as a bimodule, so over R of tensor R. So that's one way to say it. There are kind of more intrinsic ways to say it. So you could say that if I look at the endomorphism DG category of the DG category, there's the identity functor in there, and I want that to be a compact object. So I hope that answers the question. So I should say that's definitely satisfied in the case of fundamental group of a surface. So the group algebra over that is smooth in this sense. And that's related to the fact that the surface has a finite cell composition. But the language smooth comes from algebraic geometry, where basically the derived category of quasi-coherent sheaves will be smooth if and only if the scheme is smooth. But it's an abstract Morita invariant notion. Okay, so this is the setting in which we work. So let me give just a bunch of examples which are of interest. So they're higher dimensional examples, but let me focus on the two-dimensional examples. So the first example was C is local systems on this closed oriented surface. And then where does this Hochschild class come from? It comes from the fundamental class that we started with, the usual orientation. So I can map homology of the surface to homology of the free loops, because I can map the surface itself to the free loops just via constant loops. They're constant loops. And then there's a theorem, there's often a theorem. I have an abstract notion of Hochschild homology, and then I have some particular category that arises from geometry or topology. And there's some theorem telling you how to compute the Hochschild homology in terms of that geometry or topology. So here, this is the Goodwillie-Jones theorem that says, if I want to compute Hochschild homology of the category of local systems, or of the group algebra, the fundamental group, that is just homology of the free loop space. And because this taking constant loops is fixed by the circle, the image of the fundamental class will be automatically invariant. So this will be kind of by definition what we call fundamental class of the category. So that's how we make contact with Goldman's example. Let me give an example from algebraic geometry. So if S is, let's say, a K3 or a abelian surface. So that means, let's say I have a smooth projected surface whose canonical bundle is trivial, then it's one of these two things. It's either K3 or abelian. And then in this case, I let C be perfect complexes on S. So those are things which locally look like finite length complexes of vector bundles. In the smooth case, that's the same as a bounded complex of coherent sheaves. And then the Hochschild homology of this thing is computed by the HKR theorem. So this is the algebro-geometric version of this Goodwillie-Jones theorem, and it says that this is computed in terms of Dolbeck homology with shifts. So this is like this. And so the HH2, if you work out how the shifts work, this ends up being H0 of S wedge to T star S, and that's the canonical bundle. So you just choose a trivialization of the canonical bundle. You're choosing a top form that's nowhere vanishing. By definition, that's what you can do on a K3 abelian surface. And this one also turns out to be automatically invariant, somehow for dimension reasons. So this is an example from topology, an example from algebraic geometry. And let me give an example from representation theory of associative algebras. Are there any questions about these two examples?
So I guess in the algebraic geometrical case, you probably could also look higher dimensional things, but then the calculation is more complicated, or?
The calculation is actually just the same. You end up in the kind of top. You end up with a global section of the canonical bundle.
Right.
And you can even introduce some mild singularities on the variety.
Oh, okay.
So the reason right now I'm focusing on dimension 2 is that the moduli space will become more complicated in higher dimensions. So I'll state the theorem, but I'm not sure I'll have time to explain all the words in the general case.
Okay.
And here, for an example from representation theory of algebras, take Q to be a quiver. I think I don't care what kind of quiver, maybe finite. But I don't care, it can have loops. And then I consider the double quiver. So for every arrow that I had in the original quiver, A, I introduce a dual arrow, A star. And from this, I can form the so-called pre-projective algebra and also a deformation of it. So what is this? This is it's a path algebra of the double quiver modulo what are called deformed pre-projective relations. And I'll ignore signs, but let me tell you kind of roughly what this says. So it's a sum. The relations are quadratic. It's a sum over arrows in the original quiver. So I look at commutators of A and the dual arrow. And then also, maybe I want to set the whole sum to 0, or maybe I want to set that equal to some constants. And here, if I look at A followed by A star, that's a loop at some point. And so I can put a scalar at that point. And so somehow I should kind of do this component by component, kind of vertex by vertex. So I want those to be equal to 0, or I want this to be an equality. So these are called the deformed pre-projective relations. In general, depending on the quiver, you might want a kind of derived version of this, which is a little more general because somehow these equations are not transverse. But roughly it's like this. And then, so claim. The maybe derived in general, depending on the quiver, you might have to put in some derived corrections. This has a natural dimension 2 Calabi-Yau structure or orientation. And this is a little harder to explain, but one reference for it is a paper of Polak, Shirotska, and there's a third author. I've never met him, so I can't remember his name. It's with a T. So I apologize to him. And they use this is using a construction that Tobias Diekerhoff and I worked out. It's a kind of non-commutative cobordism. So anyway, there's a way to construct a natural orientation on this. Those are 3 main examples. And let me state some theorems now. So the theorem A, let's say it's theorem A. So this is with Tobias Diekerhoff. This is kind of input to the story about the string Lie algebra. So this just tells you something about the moduli space. So let C be a smooth DG category with orientation or Calabi-Yau structure. These are just synonyms of dimension D. In the examples above, all of them that I gave were dimension 2. So you can keep them in mind. And let MC be it's a derived moduli space. So it has points defined not just over commutative algebras, but over commutative differential graded algebras. So let this be the derived moduli space of objects in C. It's not actually all objects, it's kind of small objects. So Tohen and Vauquier define this moduli space. So then there's an induced symplectic structure on this thing. And if D equals 2, it's just a symplectic structure, but maybe in some stacky sense. If D is not equal to 2, this symplectic form, it's a 2 form, but because we're in a derived moduli space, that's valued in the cotangent complex. So wedge 2 of the cotangent complex. And you can shift that up and down. So a 2 form there can have a degree. So I've shifted degree 2 minus D. So when D equals 2, you don't see this shift. And on the tangent space, on the tangent complex, it gives seriduality in this category. Just like in the case of local systems, I have Poincare duality. So this is input. And what I really want to talk about is the theorem Brav, which generalizes Goldman's theorem. So I have this moduli space, it's symplectic. I have some Poisson bracket on functions. And I want to produce for you a bunch of functions that come just from the category, and I want to tell you how to compute their Poisson brackets. So the observation is that in the surface case, the Goldman Lie bracket, it lived on H0 of the free loop space. And the kind of correct interpretation of this categorically, like I said, it can be given as Hochschild homology of local systems. But in fact, kind of by the way the invariance works out, I can rotate. I can rotate a loop, and that corresponds to the circle action on Hochschild homology. So this is actually cyclic homology. And then it turns out that there's an analog of trace of monodromy for any DG category, any smooth DG category. So given any, so this has nothing to do yet with the orientation or the symplectic structure. There is a, I'll call it trace of monodromy in quotes. So it generalizes that. It's kind of really trace of action. It goes from the cyclic chains of the category to the complex of functions on this moduli space. So if this is actually a pretty tautological thing. If I define for you carefully the moduli space, we could see what this thing is. But concretely, it's the same kind of thing. I can think of C as maybe DG modules over a DG algebra, and then the Hochschild homology will look, at least in degree 0, look like that algebra modulo commutators. And so for each element of the algebra, I'll just map to trace of its action on the module. And then the theorem Brav. So this is with Nick Rosenblum. So the right-hand side has a Poisson bracket with a shift. So I want to give the left-hand side, the cyclic homology, I want to give it a DG Lie algebra structure with a shift so that this natural map becomes a map of the algebras. And so the theorem is that this exists in a natural way. So part A is that so C now should be smooth with orientation of dimension D. And then the cyclic homology, cyclic chains, with this shift by 2 minus D, has a natural structure of differential graded algebra. So how do you construct such a structure? I either have to give you an explicit complex and tell you what the bracket is in that specific model. This might not be possible. We might not have a very good model where we can write this down because it'll look like some L-infinitive structure. A more invariant thing to do is to say, well, every differential graded Lie algebra describes some deformation problem. So we need to specify the deformation problem and check that the tangent space is given by cyclic homology. So this is so this DGLA, it controls what are called exact Calabi-Yau deformations. So it deforms the category C, it deforms this orientation on it, and it deforms it in an exact way, so that somehow some homology class doesn't change. So that's part A, and part B is that these exact Calabi-Yau deformations of C induce exact symplectic deformations of the moduli space with respect to the symplectic structure that's given by theorem A, whose Lie algebra, so the Lie algebra of exact symplectic deformations, is the shifted functions with the Poisson bracket. And so since exact Calabi-Yau deformations map to exact symplectic deformations, I get a map of Lie algebras. This is naturally a map of Lie algebras. Okay. So I've stated the theorem. The time is mostly up, but I want to make just a few brief comments. Maybe I won't even write them. But are there any questions about the statement of the theorem? For example, do you see how this specializes to the theorem of Goldman? So if I take d equals 2, and I look at cyclic homology in degree 0 and functions in degree 0, this is exactly the statement of Goldman in theorem B. So, so if the statement is clear, let me make a few brief comments. So one is that I called it the string Lie algebra because Chas and Sullivan tried to generalize the work of, did generalize the Goldman bracket to higher dimensional manifolds, and they used homology of the free loop space with a shift. Our Lie algebra is theirs, but at the chain level. So if you pass to homology, it gives their what they call the string Lie bracket on the equivariant homology of the free loop space. The second comment I wanted to make is that what makes this theorem very difficult. So we had the strategy I just described about deformations. We kind of understood this right away, but we needed a bunch of compatibilities between kind of non-commutative deformations and commutative deformations. And we thought a lot of this stuff should just be in the literature and well known, and it wasn't. And so we had to rework the non-commutative calculus and the Cartan calculus and check that they were compatible under these maps. And this ended up being a prequel to this paper, and the whole thing has been long in process, but very close to getting posted. So I'll stop there.
Okay, thank you very much for the very nice and interesting talk. I think we should give an applause to Chris, virtually or directly. And I can see there is already one question in the chat by Chengfang Wang. Is there a BV structure on both sides?
A BV structure. Yeah, so this is on the left-hand side, coming from the category yes. So this is, it would not be on the cyclic homology, but just the Hochschild homology. And then this is what you would call the cyclic Deligne conjecture or smooth DG categories. And we have a proof of this. So that will be, once we get these two papers posted, we'll post a third short one that gives a version of the cyclic Deligne conjecture. And then you can ask on the right-hand side, there are kind of BV structures that appear in Poisson geometry, and how do you compare these things? So we thought about this. This is a very good question. We're not sure. You could also ask a kind of higher genus version of this. So there's actually, if I take cyclic homology, if I have a BV algebra and I take the circle coinvariance, there's a gravity algebra structure on it, is what Gessler called it. And it's probably that I more or less know for each operation what the gravity algebra structure should be on the right-hand side. But showing the compatibility, I'm not sure how to formulate this out.
Okay, are there any more questions from the audience?
I have a question.
Yeah, go ahead.
Yeah. Hi, Chris. This is Manuel. How are you?
Hi. Very well.
So the Goldman bracket actually does not require a fundamental class, right? It's just it just requires that the manifold. I mean, you can define it for an open manifold. Just requires.
Yeah, so we can do.
Yeah.
We can also do that.
So my question is, how should I think of local systems for manifolds? What's the algebraic structure?
So the way I didn't go into this because it's harder to formulate, but actually we have a kind of theorem in Brav prime, which is what to do with a manifold that has boundary. So we wouldn't do open manifolds, we would do manifolds with boundary. And then the algebraic structure is what's called a relative Calabi-Yau structure. And so you should look at local systems on the boundary and push them forward into the bulk. So that's a DG functor of induction of local systems. And there's a kind of relative orientation on that that corresponds to Lefschetz duality, which is like Poincare duality with boundary. So you can define a kind of abstract Lefschetz duality in terms of Hochschild homology and cohomology. And then everything works out nicely. You have two moduli spaces. One of them is symplectic, the other is Lagrangian and symplectic. And then you see this more general Goldman algebra in that setting.
But this is for manifolds with boundary, right? I mean,
yeah.
So
I guess I'm kind
of open manifolds, right?
So I mean, I'm not sure what the best way to say it is there. I mean, somehow, I don't know if I have to kind of choose the boundary at infinity to tell you what happens. For surface, that's probably not such a deal. In higher dimensions, this may be a bigger deal.
Mm-hmm.
So I'm not sure what in general, how to say it. Actually, you tell me, in the string topology literature, in kind of Chas-Sullivan style, is there something for open manifolds?
Yeah. I mean, just note that the construction is only intersection on the underlying manifold and concatenation of loops. Those are the ingredients, right?
For the surface, but what about in higher dimensions?
Yeah, it's the same.
Okay.
Yeah.
Okay.
Yeah.
Okay. So
there
I'll
should
have to
be.
think about it. I'm a little
Yeah.
bit worried about homotopy. And is it homotopy invariant?
It is, I believe so. Yeah. I mean,
Okay,
the
okay.
idea is to think to think of Poincare duality on the manifold, you don't think of it as a non-degenerate pairing. You just think of it as a intersection product that is compatible with the co-product of the homology of the manifold. You see?
Okay.
That's how
So
you think
I'll
of
have to think
Poincare
about
duality.
that.
Yeah.
I'll think about it. Once you introduce this coproduct, that is seeing something about commutative geometry. So it's not obvious immediately that it will have a non-commutative generalization.
Yeah.
It might.
That
So I'll think
might be
about it.
true.
Thank you.
Yeah.
Mhm.
Thank you. Are there more questions from the audience? I had one question. So in this case, you use homology, but you could also, of course, then use dually cohomology, right? And you get some results there. And for example, is there any way to relate it to the center? I mean, in algebra, you have these characteristic homomorphism. Does it play a role in this setting as well?
So it's hidden here. So you know that Hochschild cohomology with a shift by 1 has the Gershon-Haber bracket.
Right.
And this is kind of the Lie algebra that controls deformations of a category in some sense, or you could think of it as kind of infinitesimal automorphisms of the category. And what this Lie algebra actually is it's an extension of this of the Gershon-Haber bracket by something else. So the Hochschild cohomology acts on Hochschild homology, and I look at kind of stabilizer Lie algebra for that action acting on this fundamental class. So I'll get an extension Lie algebra, and that's actually more or less what we're using here. So it is kind of actually here, but you just don't see it in the way I've written it. It's hidden.
Okay, thank you. Do we have any more questions? If that's not the case, then let's thank Chris again for its very interesting and nice talk.
Thank you, Chris.
And so next week we go from Moscow to Padua. So Anna Barbieri will give a talk, and you will find the updates of the titles and abstract on the webpage as usual. So thanks again for joining, everybody.
Thank you, Chris.